Okay, so in this problem, we have two random variables x and y, which are jointly distributed according to this density function fxy equals e to the negative y in the region where y is bigger than x and both x and y are positive. And we define a new random variable z, which is x plus y, and we want to find the density function of z. So to approach such problems, what we do is use the distribution function approach, which essentially means you will start with the distribution function of z and then take its derivative to reach the probability density function of z. So the distribution function of z is by definition the probability that the variable z is smaller than the small z, and because we know that the variable z is x plus y, we can substitute x plus y instead of z, which turns out to be the probability that y is smaller than z minus x. So to find this probability, we draw a diagram and illustrate where the density is defined. So the diagram looks like this, where this is x, this is y, this is the line y equals to x, and in this region y is bigger than x, which is precisely the region where the density is defined. So now we need to find the probability that y is smaller than z minus x. So let's draw a line y equals to z minus x. So the line looks something like this. This is the line y equals to z minus x for some arbitrary value z, and the intercepts here are z. And remember, this z is arbitrary, so you can move this line downwards or upwards depending on the value of z. But we notice that z has to be positive for this line to have some intersection with this region. So now when we look at this equation here, we need to find the probability that y is smaller than z minus x, which means you have to look below this line, and the region that intersects with the density function here is this one. So essentially what we need to do is we need to integrate the density function over this shaded region. And how does that look like? So it turns out to be a double integral of the density function, which is e to the negative y, and then we need to integrate this, and notice that because of the shape of the region, we should integrate over y first, which will capture both these lines. So if we do dy first, then we need to find out this point here and this point here. So at this point y equals to x, and at this point y equals to z minus x. So clearly the limits for y are x to z minus x. And as for y, as for x should be from 0 to some point here, and because it's an intersection between y equals to x and y z minus x, you can calculate that this point here will be x equals to z over 2. So the limits for for x are 0 to z over 2. Okay. So the next step is to carry out this integration. The inner integration is simple because there is just this exponential function which gives you 0 to z over 2 negative e to the negative y with the limits from x to z minus x. and then we have dx, which becomes 0 to z over 2 minus e minus z minus x plus e to the negative x dx, which will be negative e to the negative z minus x over the derivative of this, which is just 1 minus e to the negative x, and then we need to put the limits 0 to z over 2, which turns out to be negative e negative z over 2 minus e negative z over 2 minus, when you put 0 here, we get negative e negative z and negative 1. So what we obtain from here is negative 2e negative z over 2 plus e to the negative z and then plus 1. So the next step is to differentiate this density function, this distribution function, to obtain the density. So basically fz of z would be just the derivative of this, which turns out to be negative 2 times e to the negative z over 2 times negative 1/2 minus e to the negative z plus 0, and this negative cancels out with this 2 goes with this, so we are left with fz of z is e to the negative z over 2 minus e to the minus z for all z bigger than 0. So this is the final result. So that's how we obtain the density of z when z is x plus y under the situation where the joint density function is defined over a constrained region of x and y.